top-class problem solver. The goal of this video is to help us learn to analyze the problem and communicate our solution effectively. An electron accelerated from rest by a potential difference of 36 volts is incident on a double-slit apparatus with slit separation 1.5 nanometers. For the resulting diffraction pattern, what is the angular position of the first-order minimum? The problem-solving method consists of 3 steps. The first step is interpretation of the problem. Then we devise a strategy, and then we execute our strategy. The first step of the interpretation is to identify the concept embedded in the problem. From 2 key phrases in the statement of the problem, we see that the fundamental phenomenon is electron diffraction. So, in the statement of our solution, we say that the fundamental concept is the wave-particle duality of matter. The next step of the interpretation is to create the model and represent the model in a diagram. There are 2 fundamental parts to this problem. When the electron is accelerated, it is treated like a particle. So in our model, we have the electron and the potential difference that accelerates the electron to the double-slit apparatus. Then, when the electron emerges from the double-slit apparatus, we treat it as a wave. So from this point, our model becomes that of wave interference. The third step of the interpretation is to extract the data carefully from the problem. We are told that the electron is accelerated from rest through a potential difference of 36 volts. So we write delta V is equal to 36 volts. Because the particle is accelerated from rest, we can right away write down that the kinetic energy of the particle immediately as it reaches the double-slit apparatus is 36 electron volts. For the purpose of this particular problem, we need to translate that into joules. So we use the conversion factor and we obtain the kinetic energy of the particle just before it reaches the double-slit apparatus in joules. We are also given the slit separation of 1.5 nanometers. We recall from double-slit interference that this is the D parameter in our equation. The first step of the strategy is to determine precisely what is required. We are required to find the angular position of the first-order minimum. This is the parameter theta in our model. The second step of the strategy is to construct the concept map. The concept map relates the parameters that are given in the problem and the required parameter. Once more, we recognize that this problem consists of 2 parts. One where the electron is considered as a particle, the other where the electron is considered as a wave. The relationship between these 2 is between the momentum of the particle and the wavelength of the wave. On the particle side, we can find the momentum from the kinetic energy. On the wave side, we can connect the wavelength of the electron to the position of the minimum. The third step of the strategy is to create an action plan based on the concept map. The first step of the plan is to find the momentum of the particle from the kinetic energy using classical mechanics. The second step is to use de Broglie's equation to find the wavelength of the electron from its associated momentum. And then the third step is to use wave interference to find the unknown value theta. The first step of the execution is to follow the steps of the action plan. For the first step, we find the momentum. Using classical mechanics, we write down the equation for kinetic energy in terms of the mass and the speed. But we transcribe this equation and replace the speed by the momentum. So, isolating momentum and substituting for the mass of the electron and the kinetic energy of the electron in joules, we obtain the momentum. It is useful to check your working step by step by looking at the units. So we have kilogram squared, taking the square root gives us kilogram. We have meter squared, taking the square root gives us meter. And we have per second squared, taking the square root we have per second. So this is indeed the correct unit for momentum. For the next step, we apply de Broglie's equation. So de Broglie's equation allows us to find the wavelength of the electron in terms of its momentum. So applying the momentum that we found in the previous part and Planck constant, which is a universal constant, we obtain the value of the wavelength. Once more, we'll check the unit. Kilogram divided by kilogram cancels out. Meter squared divided by meter gives us meter. Per second squared multiplied by second gives us per second, divided by per second cancels out. So we are left with the unit of meter, which is the correct unit for lambda. For the purposes of this problem, we will transcribe this in nanometers, the unit given for d. So we treat this part of the problem as a wave interference problem. We know that the path difference, delta r, can be written as d sine theta when the diffraction pattern is projected on a distant screen. We know that to find a maximum or a minimum, we will use delta r is equal to m lambda. For a first order minimum, m is equal to 1/2. So when we substitute this value of m, along with the value of lambda that we obtained from the previous part, and the value for d, which is given in the statement of the problem, we are able to calculate the angular position theta. The second step of the execution is simply to write down and highlight your final answer. We therefore write that the angular position of the first minimum is 3.8 degrees. The third step of the execution is to check your answer. When you check your answer, make sure that you state clearly what is required, that you give the appropriate unit, and that the magnitude of your answer is reasonable. We are asked for the angular position theta, and we wrote down the angular position in degrees. To check the magnitude of our answer, we take a quick look back at the wavelength. The wavelength is found to be 0.20 nanometers. This is approximately 1,000th the wavelength of visible light, which would seem to be an appropriate magnitude for the solution. Here once more are the 3 steps of our problem-solving method. Thank you for watching.